Assalamualaikum and hello to everyone. I'm Dr. Raza. So we are from Group 3 and we're doing Project 3. So we'll start with our group members. I'm Dayana Amalia binti KAMARULZAMAN. My metric number is 215115.
Hi, my name is SYAZWANI binti RAZALI. My matrix number is 217043.
Hello everyone, my name is Aurola Tristy, anak LOKOL, and my matrix number is 214967.
My name is HAFIZAH binti Muhammad RAHIM. My matric number is 217134.
So we will be presenting our Project 3 and we will start with question 1. So I will pass to SYASWANI.
Okay, I'm presenting question 1 of our MATLAB project, which is focus on plotting a 3D graph of a complex mathematical function. Okay, the main objective of this task is to visualize the behavior of the function. Okay, the function is sin square root x squared plus y squared multiplied with exponent x negative x squared plus y squared over 10. Okay, this equation combines two elements, a sine function and exponential function. The sine function introduces a wave-like behavior, while the exponential part causes the wave and magnitude to decrease as we move away from the origin. Okay, this type of function is often used in physics to model wave motion with damping, such as in vibrating membranes or heat diffusion problem. Okay. Okay, we start by define our domain using this comment. Okay, as you can see, I this is x equal to linear space negative pi pi 100. Okay, which is negative pi is minimum, pi is maximum, and 100 is the increment. Okay, this means we are generating 100 points between negative pi and pi for both x and y axis. Okay, next we use the mesh grid function to generate a grid of coordinates. Okay, it is necessary to evaluate the function of z at every combination of x and y value. Okay. Next, we compute the function z using element wise operation. We use the dot operator to ensure that each element is processed individually, and the expression square root x squared plus y squared is to calculate the radial distance from the origin of each grid point. Okay. Okay, once we have the data, we use the surf command to plot the 3D surface. Okay, after that, we add labels and visual enhancement, which is we include a title as labels and color bar. Also, we use the color mate. We use color mate Aurola. We also set the viewing angle to 60 and 30 so that the 3D shape is easy to observe. Okay, next is the light tone and shading in the comment. We use it because we want to improve the lighting and smoothness of the surface. Okay, finally, we use existing violin and set to define the axis. All of these steps combine to produce a clear and informative 3D plot that shows how the function behaves across the XY plane. Okay, the equation not only tests our MATLAB skill in 3D plotting, but also depends our understanding of how mathematical expression can be visualized and interpreted through simulation. Okay, I think that's all from me. Thank you, and I'll pass the question to Dayana Amalia.
Next, so for question 2, I will explain this MATLAB coding that calculates both simple and also compound interest. So let's go step by step. We start with function calculate underscore interest. So this function takes all input values. So first of all is the P, which is the principal or starting amount. Next are the annual interest rate in percent. Next, N, the number of times interest is compounded per year. And the next one, T, the time in years. So our goal is to calculate two outputs, which are simple interest and compound interest. So inside the function, we first convert interest rate from percent to decimal, because calculations work with decimal values. So we divide R by 100. And then we calculate simple interest using the formula simple underscore interest equals to P multiplied by R underscore decimal multiplied by T. So this is based on the standard formula, which is simple interest equals to principal multiplied by rate and also multiplied by time. So next, we complete compound interest using this formula in the MATLAB code, which is compound underscore interest equals to P multiplied by in bracket 1 plus R underscore decimal over N to the power of N multiplied by T minus P. So let me write that down. First, R underscore decimal over N is the interest per period. Next, N multiplied by T is the total number of compounding periods. And then we use 1 plus R underscore decimal over N to the power of N multiplied by T to calculate the growth factor. And multiply by T to get the total future amount. Finally, subtract T, get only the interest earned. Okay, now let's look at the second part, which is the main program. So we define example values for P, R, N, and also T. So in this case, 2,000 is for the principal, 4.5% is the annual interest, and also compounded twice a year and for 5 years. And then we call the function simple underscore interest, compound underscore interest, which is equals to calculate underscore interest in bracket P, R, and T. So that line executes the calculations and stores the result into the variable. Finally, we print the result clearly using a printf statement, and then this displays the principal, the interest rate, the time, and also how often it's compounded, and lastly, the simple interest and compound interest values. So everything is displayed with 2 decimal places and format neatly in Ringgit Malaysia. And that is all for question 2. Now we're moving on to the third question.
Okay, for the third question, I will explain how to solve a system of second order ordinary differential equation, both analytically and numerically using MATLAB. So the first part, for part A, we are given 2 second order differential equation. The first one is ODE1, which is d square y1 over dt square plus 3 dy1 over dt plus 2y1 equal to cos t. For ODE2, d square y2 over dt square minus 4y2 equal to sin t. Next, in this part, we are also given this initial condition. y1 0 equal to 1, y1 double prime 0 equal to 0, y2 0 equal to 0, y2 prime 0 equal to 1. In this part, we use symbolic variables in MATLAB to define and solve the ODEs analytically. We declare symbolic function y1t and y2t using sims. Then we define the two equations using the diff function for derivatives. We also set up the initial conditions properly using the subs command. Finally, we use dsolve to solve the system symbolically and display the solution using pretty for better formatting. This gives us the exact expressions for y1t and y2t. Next, we move to part B. Part B asks us to converting to first order and using ODE 45. Since ODE 45 in MATLAB only handles first order systems, we need to convert both second order equation into a system of first order ODEs. So, we define the state vector as x1 equal to y1, x2 equal to dy1 over dt, x3 equal to y2, x4 equal to dy2 over dt. So the systems becomes x1 prime equal to x2, x2 prime equal to negative 3x2 minus 2x1 plus cos t, x3 prime equal to x4, x4 prime equal to 4x3 plus sin t. We define this system in a function handle called ODE fun. Next, we set the initial condition 2 into 1, 0, 0, 1, and the time interval 0 until 10. Using ODE 45, we solve the system numerically and extract y1 and y2 from the solution. Finally, we plot both y1 and y2 to visualize the numerical solution. Next, for part C, the question asks to comparing analytical versus numerical solution. In this part, we compare the analytical solution from part A with the numerical results from part B. First, we convert the symbolic solution sol y1 and sol y2 into MATLAB functions using MATLAB function. We then use ODE 45 again to get the numerical solution just like before. Next, we evaluate the analytical solution at the same time points as the numerical solution using the function handles. Then, we plot two graphs, one for y1t and another one for y2t, each showing both numerical and analytical result for easy comparison. For the final part, which is part D, plotting absolute errors. In this part, we will compute and plot the absolute errors between the analytical and numerical solution. We do this by subtracting the analytical values from the numerical ones and taking the absolute values. Then we plot the errors for both y1 and y2 on the same graph. This helps us visualize how accurate a numerical method is. In this case, the errors are quite small, which shows the ODE 45 is performing well. So this is the output of the coding for question 3. This is the graph, numerical solution of y1t and y2t using ODE 45. This two graph is the comparison of y1t and y2t. And last graph is the absolute error between analytical and numerical solution. That's all from question 3. We will move to question 4.
For question 4, I will explain how we want to solve one-dimensional wave equation using MATLAB and the finite difference method. We are solving this partial differential equation del square u over dt square is equal to c squared del square u over dx squared. This describes how a wave behaves over time. So for step 1, we define the problem settings like L, T, C, and X, and NT. For L is equal to 1, T is equal to 1, C is equal to 1, and X is equal to 50, and NT is equal to 100. And for step 2, we set up the grid. For the grid, we divide space into 55 points, and X plus 1, we divide time into 101 points, and T plus 1. We use linspace to create vectors for space and time grids. And step 3, we want to check stability. For stability, we use R is equal to C times dt over dx, and R2 is equal to R power of 2. This value R is important to make sure the method is numerically stable. The rule is stable if R less than or equal to 1. And step 4, we apply initial condition. The initial shape of the wave is ux0 is equal to sine pi x. The wave starts like a single sine bump from x is equal to 0 to x is equal to 1. Then we use a MATLAB code like this that we present in the slide. And this calculate the next step using the wave equation, assuming initial velocity is 0. We use a finite difference formula to do this. And for step 5, we use loop over time to calculate the wave. We use loop for n with the end. This part use the finite difference method to simulate the wave for every time step. Each new point in time is calculated based on 2 previous time steps. And for step 6, we want to print table of result. We use fprintf. We display how the wave value changes at different x position for 3 times. We start with t is equal to 0, t is equal to 0.5, and t is equal to 1.0. This helps us to see the wave movement numerically. And last but not least, we plot the 3D surface plot. We use mesh grid and surf for 3D surface plot. This creates a 3D plot showing the wave as it moves over space and time. And the surf command plots how the wave shape changes. So the axis is x for position, t for time, and we use z for displacement, which is wave height. This is the output for the question 4. And this is the graph, which is wave equation solution. So I think that's all from our group, which is group 3. Thank you.